Hello, everybody. This is Team 1115, and this is our project for testbed for Wind Turbine Blade. In the team, we have Trevor Ellis as the engineering team leader, Sean Bertram, Scott Burleson, Michelle Hogan-Poole, John Hernandez, and myself, Kang Pham.
For our project, our team was tasked with designing two test beds for offshore wind turbine blades. The first test bed was for testing the dynamic response, or the natural frequency, while the second test bed was for the static characteristics such as deflection and strain.
The first test bed is designed to allow for the testing of the natural frequencies of a wind turbine blade. To do this, the blade will be attached to a seismic mast which will rest on EVA foam to simulate a soft spring boundary condition. The soft spring boundary condition is used to simulate the tower of the wind turbine flexing under stress. This will allow our client to better understand how each individual blade will behave in relation to the whole wind turbine system. The seismic mast can also be set on the floor to simulate a fixed boundary condition. The natural frequencies of the blade will be excited by a shaker that will shake the blade back and forth rapidly, and the blade's response is measured using a laser system that is provided by the client.
The seismic mast had to be designed so that the rigid body modes of the system would be as low as possible within the specified budget. There are two ways to lower the frequency of the system. First, we can make the seismic mast heavier, or second, we can get supports that have a very low stiffness but sit under the seismic mast. After research and simulations in the software ANSYS, the final design was to go with the seismic mast that weighs 1,300 pounds. We support the seismic mast with EVA foam, which has a fairly low stiffness, but can support the mass of the system. The other requirement was to design a 4-meter blade fixture, which has to attach the blade to the top of the seismic mast and withstand cyclic loading. The shaker table is a table that is able to hold the shaker at a height of 2.5 feet to a height of 6 feet. This will allow the shaker to agitate the root of the blade as well as the center of the mass of the blade.
Testbed 2 is used to test the static characteristics of the blade, such as strain and deflection under different loads. To do this, we designed an apparatus that is attached to the top of an optical table, which was provided by the client. We were only tasked with designing this testbed, so unfortunately, we did not get to build it. The testbed works by using actuators to apply loads in the flapwise, edgewise, and torsional directions to the blade, and then the blade's response is recorded through the use of strain gauges and displacement sensors, which are provided by the client.
So the requirements for testbed 2 was that we had to be able to apply forces in the flapwise, edgewise, and torsional directions to the blade without actually damaging the blade itself. So we designed the blade clamp, which encases the end of the blade in foam, and it allows us to attach the actuators to the blade without causing damages to the blade. The actuators are responsible for applying the forces in all 3 directions to the blade, and they are connected to the actuator fixture as shown in the picture, and the blade clamp as well. The blade fixture is simply responsible for holding the blade in place at the end of the table.
So next we will be moving on to the demonstration of testbed 1. Here you can see a picture of testbed 1 with me standing next to it. As you can see, we have the seismic mast sitting on the ground with the fixture that attaches the blade to the seismic mast, and the actual blade is around 4 meters tall, so it's a very big system. Now, in order to measure the natural frequencies of the blade, we have 3 laser heads located here, here, and here, and these are all pointed at a specific point on the blade, and they are measuring the vibration of the blade at that specific point. So we can see that the lasers are currently focused on this specific point on the blade that is shown by the green dot. And here's the shaker that is actually shaking the blade back and forth, agitating the natural frequencies of it. At the end of the shaker is also a force and accelerometer gauge, which tells us how much force and acceleration the shaker is actually applying to the blade at any given time. And the shaker is actually running in this video. It's very difficult to see because the shaker doesn't move very much, so we placed a water bottle on top of the shaker just to show that the shaker is in fact vibrating the blade right now. Then all of the data from the shaker and the laser heads is sent to this computer, which then processes the data to get the natural frequencies of the wind turbine blade. So in this window, we can see what the laser head is seeing. This essentially shows all the points that have been scanned already, as well as all the points that still need to be scanned. In this window, it shows the raw information from the laser head scanner about how the blade is displacing at that specific point. And then from this raw signal, it takes a Fourier transform of the signal to extract the natural frequencies of the blade, which is shown in this window. And it does this process for about 700 different points on the blade to get a full simulation of the natural frequencies of the whole wind turbine blade. Now, the first test was done with the seismic mass sitting on the ground. This is to simulate a fixed boundary condition for the root of the blade, but the seismic mass can also be placed on EVA foam, which allows us to simulate a soft spring boundary condition for the root of the blade. The purpose of this is to understand the dynamic response of the blade under different boundary conditions. And the reason we're doing this is to compare the real-world tests of the blade to the computer simulations of the blade that can be run in software like ANSYS. So next we're going to talk about Testbed 2, which our client wanted us to design, but he wanted to wait until a later date to build and fabricate the final design. So we have the final CAD model of the design that we're going to show you. The purpose of this testbed is to put flapwise, edgewise, and torsional loading on the blade, and then measure the strain and displacement of the blade with those forces applied. So back here we have the blade fixture, which is pretty simple. It's meant to be bolted to this optical table, which was provided by the client. And all this has to do is be strong enough to hold the blade in place when we're putting forces on the blade. Then next we have the actuators themselves, which are pneumatic actuators, which means that they are operated by compressed air. So you can put compressed air on the bottom inlet as well as the top inlet to make the actuator move up and down as you need it to with however much force you need it to. And the client actually has air pressure regulators in the lab that we can use to mount into these holes to regulate the amount of pressure that's going in there and thus the amount of force that the actuators are putting on the blade. So these two actuators are the flapwise actuators, which essentially means that they can provide a flapwise force or a torsional load. You can do a flapwise force by making these two actuators operate in conjunction with each other. So, i.e., both are pulling the blade down or both are pushing the blade up with the same amount of force. Or you can have a torsional load by having one of these actuators push up while the other is pushing down. And that will create a moment around the center of the blade. And then this actuator on the side is the edgewise actuator, which essentially creates a force on the edgewise direction of the blade. And then this part right here, highlighted in green, is the blade clamp. And this part will have pink insulation foam wedged between these two C channels and the blade. This to make sure that when the actuators are putting force on the blade, it doesn't harm the blade. You'll also notice that these actuators look like they're going through the blade. This is because this is what the actuators look like when they're fully extended. And where they're fully retracted, they'll be along this length. Another thing to note is we have these inline ball joints, which is essentially like a ball and socket joint, which operates much like your shoulder does. Like you can rotate it around any direction that you need to. And these will be screwed into the bottom of the C channel here. The reason why we have these is so that when the blade undergoes a torsional load and it starts twisting, this will allow the blade to twist without putting unnecessary forces on the actuators itself. We also have another ball and socket type joint on the edgewise actuators to allow the blade to flex up and down as it needs to. And then this bolt will actually be put through this ball and socket joint. And then the final thing is the actuator fixture, which essentially connects the actuators to the optical table through this yellow plate here, which will be bolted to the optical table and will be used to mount these angled pieces to this aluminum, which supports this edgewise actuator here. And that is our demonstration. Thank you for watching our presentation. We will now open the floor for questions.